All right, so this is lecture 5, coming from week 3. What we're going to do today is apply the differential equations that were derived previously to some examples. And first, Dr. Belhoff looked at she reviewed the Fick's first law of diffusion, which you'll obviously need to know very well for the exam. This is Fick's first law of diffusion. This is it in one direction, and so that's what you'll be using in the exam. I'm sure you won't be doing anything in two directions. J, in this case, is the molar flux, and D, of course, is the diffusivity of component A diffusing through species B.
Which we look up in a magical book somewhere.
Right. Or we had a correlation where you could estimate that in a previous lecture. And of course, these are the equations. The most important slide is this one, where we have assumed constant density and constant diffusivity, and broken it out into concentration. And so here is the time component, here is the bulk flow component, this is the diffusion component, and this is the reaction. And of course you've got the different coordinates here.
And that's slide number 5, lecture 5.
Then she talked about the different kinds of conditions if you have a non-steady state. So you're changing with time, then you need an initial condition. If you have, if you do have steady state, you do not need an initial condition.
Because it doesn't matter, it's the same no matter what time you start at.
Right. These boundary conditions that she's talking about here are spatial. So if you have a second derivative with respect to z, for example, then you'll need two boundary conditions on known locations of z. For example, the center line, or a place of symmetry, and the surface are typical. So she talked about different types of boundary conditions, like a known concentration, a known surface boundary where it's reacting, a known flux, or here we know how much is being convected in or out at a boundary, and we'll be talking about that after the exam.
I know that boundary conditions was something that people seem to have a lot of questions about.
Mm-hmm.
And the way I think about spotting boundary conditions, I'll just throw it out here and see how you feel about it. So I look for a couple of things when I think about the situation spatially. I think about, can I find symmetry of any kind? Linear, radial, anything. Can I find places where things are standing still? Sometimes that's in the middle of something, and it kind of ties with symmetry. Can I find places where things are touching other things, and I know what's going on when they make contact?
Right.
And can I find places where things are going in or coming out? So those are places where I usually look for boundary conditions. And if there's any more that...
No, that's a great summary. Yeah. And here are some common boundary conditions similar to what we just talked about. A known concentration at a particular place. The mass flux is specified. Maybe it's specified at a surface, or maybe it's 0 because you've got some symmetry, like you're at the center line of a sphere, or the center of a sphere, or the center line of a cylinder.
And everything's symmetrical, so you wouldn't need the...
So the gradient will be 0, which is the same thing as saying that the flux is 0. Or maybe you have an impermeable surface, so nothing could be diffusing into it. And once again, the flux is zero, so the gradient is zero.
And I do want to point out this boundary condition stuff. I'm an electrical engineer. I've never done biomedical stuff. I've actually never taken biotransport.
Mhm.
So a lot of this is how do you translate between math and real world things? And it applies to all sorts of systems. And here you've got math and soon fluids and heat, but it applies to like, electrical systems in my case and many other kinds as well.
Right, right. Look at it physically. What's going on physically? And try and relate that to a mathematical boundary condition. Let's see, she's got a specified reaction rate in here as an example. Once again, here's convection, and here's an equation that we'll be talking about after the exam, so you don't have to worry about that right now. What kinds of problems can we solve using these tools in mass transfer? And she showed an example of air going into an alveolus, and the air then has to go from inside the alveolus, and it has to diffuse through several different things to get into the blood. Okay, I guess that's the main point of this example. And so she's applying the rectangular coordinates here in a very loose way, just to kind of get an idea of what's going on with that system. And let's see, I think she was talking about that there's some convection going on. There's also diffusion going on. There's some reaction going on, oxygen being consumed, oxygen being taken up by the blood cells, and of course it's not steady state. And so she asked what factors in these equations could be affected for different kinds of people. Someone mentioned a smaller person, the dimensions would be different. Someone with cystic fibrosis, the diffusion would probably be different, plus the thickness of the mucus that it had to pass through would be different. So you would look at the different physical forms of the geometry and what factors might be affected for a person with sickle cell disease. And I cannot recall what she said, but to me it would be perhaps the oxygen might not be picked up quite as fast.
And it's pretty cool because like you can model all sorts of things with these equations and then come up with, perhaps heart-lung machines. You'd have to figure out how lungs work so you can replicate that effect in the devices that you're making.
Right. It applies, to the world. Anything you can come up with. So what we're going to do now is we're going to take this general differential equation and we're going to come up with boundary conditions, apply them, and then we'll be able to solve for what the concentration looks like everywhere within the system.
I will also say the first two skills, if you go to a graduate school in any STEM field after this, you're going to use over and over and over. Mm-hmm. So this type of class is a good type of class to learn how to do.
Right.
In terms of strategies for studying and learning this type of material and this type of operation.
Right. And then once you've gotten this far, you can either solve for the concentration profile analytically, or you could take it to MATLAB or solve it numerically. Okay, so here we have an example of a spherical droplet of a solution that's got some type of solute that is volatile and is evaporating out of the spherical droplet and into the surrounding medium. And what we want to do is to find the concentration within the surrounding medium. Okay, so it contains a supersaturated solution of something, which it doesn't matter, it's a solid or a liquid somewhere in there. And it's in the droplet at that concentration. It is evaporating into the surrounding medium.
And and it's stagnant.
Oh yes, and the medium itself is stagnant. And what we're supposed to do is look at the steady, so it's steady state. Actually, it's kind of pseudo steady state, but we'll say at this point in time it's steady state.
Close enough.
Into the surrounding medium, the surrounding gas. Okay, so there's no bulk flow, which means that all the velocity components are zero. There's no reaction, so that's zero, and it is steady state, so that is zero. So we come here and go to that lovely slide with the equation of continuity, and we're going to pick it up in the spherical coordinates. We know that it's steady state, so that is zero. We know that the velocity is zero everywhere, so all of these velocity components are all zero, and so this entire left side is zero. Okay. On the right side, let's see, over here we have no reaction rate. And also, we're going to assume that there's no change with regards to theta or phi. So it's just a function of radius. So we've got diffusivity times 1 over r squared d by dr. And I can use a d now instead of a partial because it's only varying in the r direction. R squared dCA dr.
Close parentheses.
Oh, yes, thank you. I'll make this a square. All right, and so now I can divide by the diffusivity on both sides, and multiply by r squared on both sides. And I'm going to multiply, I do this a little bit differently than the others. I multiply by dr. And so on this side, I just get d r squared dCA dr is equal to 0.
So you've swapped sides there, but yeah.
Yes, I did. And this looks a little ugly until you decide, okay, let's just say y is equal to r squared dCA dr. So this equation just becomes dy is equal to 0. I take the integral and, come on up here, y is just equal to C1.
But C there is just some constant, not concentration. So I might actually use a different letter or draw a smiley face or something so I don't mix it up with the concentration stuff in this case.
True.
And y is also
Yeah.
insert arbitrary variable here. Nothing special about y.
Right. Let me just put this back here. You didn't have to do it to this detail. I just did that so that people could see how I did that integration. All right. And let me divide by r squared, so I'm going to divide by r squared and multiply by dr, so I get here dCA is equal to C1, let's see, C1 over r squared dr. All right, and now I can integrate this. And moving on, I get CA is equal to minus C1 over R plus C2.
That's
Okay.
not very scary.
That's not scary?
No.
No. All right. And in the lecture, Dr. Belhoff took that negative sign and she just folded it into C1 because it doesn't matter. It's some constant. I don't know what it is yet. So it could just be negative, a negative number. All
I'm
right.
just thinking about what the math here physically means, just checking if it makes sense physically,
Mhm.
which sometimes I tend to make careless errors in my algebra sometimes, so I always look at my answer at the end and go, does this make physical sense? And so here, as R gets bigger and bigger, so as we go further out from that droplet, which I'm kind of imagining like floating in a space station or something,
Mhm.
CA drops, which makes sense. Like the farther away from the droplet, the farther away it is, the less it's able to diffuse out.
Right.
So
And it'll be easier to see once we put the boundary conditions in,
cool.
which we haven't talked about yet. Let's talk about the boundary conditions. Okay, so we need two boundary conditions here. We've got two constants of integration, so we need two boundary conditions on Z. And since we're looking in this gas out here, we need some locations. One of them will be on right here on the surface of
Yep.
the sphere. And the other one, I don't have anything really clear, so I'm just going to take at Z equal infinity way out here. Oops, excuse me, R. I forgot what R is equal to infinity. Okay, so at R equal to infinity, what do you think will be the value of the concentration?
There's nothing there. It can't get out
Right,
that far.
it hasn't gotten out that far. So we're going to say that's one boundary condition. I'll call it, I forget what sheet, whether that was boundary condition 1 or 2. I'll call it 1. So there's one of them. And the other one is right here at the surface. What we have going on is Henry's law. And so the, we're using PSAT. I'll make sure I do it the same way that she did it. Maybe you can, yeah. Can you cut this part out?
Yep.
Please do. Yeah, okay. So the way she did it, she used the fact that it's a saturated evaporation here. So the concentration at the surface, and she called it CA, I'll call it CA surface, is equal to PA sat over RT. I can't.
Over
RT. All right. So this is very ugly. Let me rewrite it down here where I have space. I've got boundary condition 1, where at R equal infinity, CA is equal to 0. And I've got boundary condition 2, at R equal to the radius of the sphere.
which we've just made up a variable for.
CAS. Okay, actually she called it CR. I'm going to call it CAS, it doesn't matter. All right, so let's plug those in. Let's see, let's start with boundary condition 1. So CA is 0 at minus C1 over infinity plus C2. So in this case, C2 must be 0.
Cool.
We'll plug in boundary condition 2. So CA at the surface is equal to, let's see, minus C1 over R. So C1 is equal to minus RCAS. Is that right? RCAS.
Yep.
CAS. Okay, and I'm going to go on to the next slide and plug this in. Let's see, CA. It's hard to write on this thing. CA.
I need to load the screen.
Okay, I'm going to have to plug it in here. CA is equal to, C2 is 0, and I've got minus C1 is minus R CAS, something's wrong there, over R.
And we can have the minus signs cancel each other out.
Yeah, that's right.
Awesome.
That's right. Okay, so CA is equal to CA at the surface times big R over little r.
And again, checking to see if this makes intuitive sense and physical sense.
Mm-hmm.
At big R, which is the surface of your zero gravity floating sphere.
Mm-hmm. So if this is
Big
equal
R
to
over big
R,
R would be 1. So CA would equal CAS. Cool.
Mm-hmm.
And then as R goes to infinity, this does in fact go to 0.
Whoops, goes to 0. That's
Yep.
right.
And so this
Okay.
this feels pretty good to me if I think about what the math translates to in the real world.
Right, and it's going to be something like CA versus R. It's going to be something like that, approaching 0.
As it drops off.
Mm-hmm.
Yep, and so notice that we've only solved for what's happening in the stagnant gas around us. So if the gas starts moving, if there's a fan blowing or wind, stuff changes.
Exactly.
Right, and we know nothing about what's going on inside the sphere of whatever substance we have.
Okay, then she took this equation. Let me rewrite it here because I've lost it. CA equals CA surface times big R over little r. She took this equation to calculate the rate of mass transfer. Okay, and let's see. So the first thing, what we're going to do is we're going to find the flux at the surface. So that we can know at what rate is this sphere putting this material out into the gas. So that is always equal to, you've got this memorized, minus the diffusivity times the gradient. And that's going to be at the surface. Okay, and if we do this, if we take this and take dCA, dr is CAS, r, and let's see, I didn't leave myself space, so I'll do it here. Minus 1, can I take the derivative? Minus, there we go. Did I do that right? No, I didn't. Yes, I did. Okay. Okay, and so if we make that at r, we end up with minus Ca at the surface divided by r. All right, and I've forgot my diffusivity. No, so the flux at the surface is just minus the diffusivity times this. So it's the diffusivity times Ca surface over R. Okay, and then the rate is just the flux times the surface area. Okay, the flux is diffusivity times the surface concentration over R. Whoops, that's not showing up, over R, times the surface area, which is 4 pi r squared. Okay, and you can pretty that up. This cancels, so you've got 4 pi.
Big R.
I'm running out of space. Diffusivity times CAS. I shouldn't have tried this. CAS R. Okay. All right, and that's as far as I'm going to take that one. Let's see. Then she talked about, once again, we're looking at a sphere, only this time we have a spherical particle with a homogeneous reaction. So something is diffusing into the sphere, and it is being reacted inside the sphere. Okay, the concentration is somehow maintained at the level CR is, so here, as she wrote here, the concentration at the surface is maintained at a constant level, and that's really nice. The average rate of consumption of A is given here as a constant, and the question is what level must this be in order to maintain that reaction rate?
So I'm trying to think about what kind of situations might approximate something like this, and
Perhaps this is a cell or a sphere of cells. Okay, it's a little bit contrived because the reaction rate is constant.
but if we have, let's say it's a cell and it's surrounded by something that we want to get into the cell and keep on reacting within it.
Right, like oxygen or glucose or something.
Right. So in that case, let's say oxygen. So what level of oxygen must be surrounding the cell at all times to keep up with that reaction rate?
Right. We're going to assume they didn't say anything about steady state, but we're going to assume that.
Close enough.
And here's a big assumption that the reaction is the same. The rate is the same everywhere in that sphere. That's not a very good assumption, but we're going to go with that. The diffusivity is constant and there's no bulk flow. So,
well, that would be if the sphere is very, very, very small. We could kind of say it's sort of homogeneous-ish.
Possibly. Possibly. So once again, it's a sphere, so we go to our favorite slide now, the equation of continuity of A, and apply our assumptions. There's no change in time because it's steady state. There's no bulk flow. You notice how always on our equations we always get 0 on the left side.
Yay!
So far we've been able to do that. Let's see, we have a constant reaction rate, so we can't get rid of that. But we're going to make the same assumption that it's only a function of R. It doesn't change with theta or with phi. So once again, we get this equation, diffusivity times 1 over R squared, d by dr, R squared dCA dr. Only now we've got the reaction rate here. Okay? And let's see. What Dr. Bellhoff did is she said the reaction rate is going to be negative. So instead of making this a plus, I'm going to put the negative sign here. And so that's fine as long as you can follow along with her in that. Okay? So I made a mess here. But she said it is plus A or A, but it's being consumed, and so this is negative, so she put the negative there. And let me rearrange this a little bit. I'm going to put the reaction rate on the other side and divide by diffusivity, multiply by R squared. And so then I get d by dr, R squared dCA dr is equal to RA over the diffusivity times R squared. All right, let me do one more thing. I'm going to take this dr and pull it over here. And now I'm ready to integrate right there. So now I've got R squared dCA dr is equal to RA over diffusivity. What is that? R cubed over 3 plus C1. Okay, and I'm going to divide by R squared to get dCA dr is equal to RA over 3 times the diffusivity. Let's see, I divided by R squared, so I get R plus C1 over R. All right, and now I could go on, but at this point I'm going to pause. And I have a bad habit, I should be specifying the boundary conditions at first. But let's talk about one of the boundary conditions here. This is a sphere, and we're looking at the inside of the sphere for this problem. And so at the inside of the sphere, we have r equals 0. We can use that as one of our boundary conditions. And again, we know from symmetry at the center line or at the center point, there's no flux, there's no gradient. So my boundary condition is going to be, let me write it here. Boundary condition 1 at r equals 0, the gradient is equal to 0. So if I apply this here, 0 is equal to RA over 3 times the diffusivity times 0 plus C1 over 0. Well, the only way that can be true is if C1 is equal to 0. So now dCA dr is equal to RA over 3 times the diffusivity R.
Yep.
And once again, let me pull this over here and integrate.
Yay.
And I get CA, I'm going to run out of space, CA is equal to RA over 3 times the diffusivity R squared over 2 plus C2. All right.
So now we need a second boundary condition to get rid of that second constant.
That's right. And we're going to just say here's my boundary condition. I need space over here. Boundary condition 2 at r equals big R. That's the only place we have left, the surface. We're just going to specify CA is equal to, Dr. Bellhoff called it CR, or previously I called it CAS.
Yeah, I think if we go
I'll go
to the
CR.
up to the slide, it was
Yes, that's right.
concentration of A is somehow maintained at the level CR magically.
So that's a given. Yeah, I forgot about that. All right, so there's our boundary condition. And if I apply it, I'm going to stick it down here. CR is equal to RA over 3 times the actually it's 6 times the diffusivity. I'm sorry, it's so messy. Capital R squared plus C2. So now I need to come on down here. C2 is equal to CR minus RA over 6 DAB R squared. And now I can plug that into my equation. CA is equal to RA over 6 DAB. Little r squared plus CR minus RA over 6 DAB capital R squared. And you can make this as pretty as you want. I would love to pretty this up a whole lot to make it more beautiful, but I'm going to refrain that from that. I'll just say, RA over 6 DAB big R squared minus little r squared. Okay.
And again, that only applies to inside the sphere now. So notice that for the boundary conditions for the first one, we went out to infinity because we were concerned with the gas surrounding the sphere and going out. And that's actually one I forgot in my list of boundary conditions to look for. It's like infinity is another one, going very, very far away.
Not our favorite, but sometimes we have to use it.
Yeah, and then here we're looking inside, so we had the center as well as the surface of the sphere.
Okay, so what we did today is focusing on spherical coordinates for this lecture. Other coordinates will be focused on in the upcoming lectures. And we solved the differential equations of mass transfer. We were able to simplify it by making some assumptions.
Namely, that things are steady state, that there's no flow.
Right, and that it's only happening in one dimension.
Everything's symmetrical. Because it's a sphere. We like spheres.
Yes, it's not just because it's a sphere, but because it's a sphere where things are only changing with r.
With radius.
Right. In real life, of course, that might not be true, in which case you can't come up with a beautiful analytical solution like we did, and you'd have to go to numerical methods.
Oh.
Okay, but this is, we're just learning this equation, and so we're simplifying things.
And we did a lot of founding boundary conditions here, I think, and
Right.
seeing how they went from the physical setup to, oh, this means that these must be the boundary conditions for our math.
Right. So, and one thing we looked at was we had two examples of a sphere. One is where we're looking at the medium outside of the sphere, and one where we're looking at the medium inside the sphere.
Right, and so for the one where we were looking at the outside of the sphere, our boundary conditions were infinity, where I can write really far away, and then
At the surface.
and at the surface, because we have no idea what's happening inside. And then the one on the inside, our boundary conditions were at the center and at the surface, because we don't know what's happening outside.
Right.
Yeah, question marks.
And what you didn't see, because Mel is going to be editing it out, is when I started solving one problem, for example, this one problem, then I forgot that I was looking at the external medium, and I started solving it for the internal. So be careful with that. Make sure you remember where you're at. Are you external or are you internal? Don't make the mistake that I just did and made Mel have to edit the video.
But it happened, right? We've had how many years of grad school between us? Probably way too many.
I don't want to even think about that.
This is getting edited roughly in a lot of takes, because we still make these kinds of bloopers.
Yes, so be careful.
Yeah. All right. Good
That's
luck.
it.
That's lecture 5.